So I'd like to introduce Mike Fingeroff. He is a HLS technologist for the Catapult HLS platform in Siemens EDA, and he's been doing that since 2002. So quite been with us a while and doing that, quite the expert. Area of interest include machine learning, DSP, high performance video hardware. And prior to working for Enter/Siemens, worked as a hardware designer developing real-time broadband video systems. Okay. So Mike, do you want to take over?
Yes, Ellie. I'm trying to start my video, but maybe, oh, here we go. Okay, let me just share my screen here.
Okay, I will stop my video.
Okay, how does that look?
That looks great, Mike. We can see
All
it.
right.
Good.
So this is going to be a quick review, just kind of a high-level overview of what HLS does, and and why that's really powerful. And we're going to provide links for training material and stuff like that that will go much more in depth. But for people that aren't that familiar, this will give you an idea about the power of HLS. And then for those of you that are familiar with HLS, it will be a review of stuff that you already know. So let's get going here. So we'll talk about the benefits of HLS, why Catapult HLS is a good fit for building complex SOCs, and then we'll wrap it up with a quick summary. So Catapult HLS is definitely by far the best solution to rapidly go from an algorithm to high performance hardware. So one of the big parts, and I'm going to focus more on the design side of things, and we'll get into the verification, but with high-level synthesis, you can make very late-stage functional changes to your design without impacting design schedules. So a lot of times, algorithm engineers may come up with a better version of an algorithm, and if you're doing a hand-coded RTL design flow, it may be too late to incorporate that into the next version of the chip. It's also very easy to switch between technology nodes. You may be prototyping in FPGA and then going to ASIC, and that's simply changing a constraint in the high-level synthesis tool. Ellie had talked about this. You get to do architectural exploration for exploring power, performance, and area. And so you have a single source that you can create multiple performance targets to get the best possible result. And ultimately, this is about accelerating the design time, really the entire design flow. And it's because we're doing everything at a higher level of abstraction. So we're going from, a year down to a few months to get your chip out. You get to add new features in days, not weeks. And ultimately, designing and debugging is easier because it's much less code than hand-coded RTL. So debugging C or System C is far easier doing that in an integrated debug environment than having to debug at the RTL level. So a quick poll, what is your current design target that you're working on? You're working on ASIC, FPGA, both, or other?
Okay, don't forget to hit submit once you've made your choice. All right, gonna end it in a second.
All right, so almost, well, a little bit more doing ASIC than FPGA, and about a little less than a third doing both, and then 7% doing others. So that's, yeah, I think as we would expect. All right, let's get into the meat of what HLS is really doing for us. So Catapult can synthesize either pure untimed C or C++ or System C to RTL. And one of the advantages here of why HLS is so powerful is that when you're doing complex SoC designs, it's easy to get the hand-coded RTL wrong. So you're taking a spec, you're implementing that in RTL, and it's very possible to introduce bugs into the design flow. And so Catapult now, we've had a production tool for close to 2 decades. It's a very mature synthesis tool. So we like to call the Catapult's RTL correct by construction. And what I mean by that is that 99.99% of the time, we're not going to make a mistake. So you can describe your design in either C, C++, or System C, and Catapult is automatically going to synthesize RTL, a timed piece of RTL that has the same functionality described in your C code. So there is no RTL debug. You get to focus on refining your design, and then the verification team simply is going to focus on doing coverage closure, not having to debug the RTL. So that's one of the very powerful features and a big time saver. You get to simulate the real hardware behavior in C++ and System C, and we're going to focus a lot on this when we talk about MatchLib. But also part of this simulation is going to be for simulating precision using bit-accurate data types. And so, again, doing today's modern SoC designs, these can be very computationally complex. We're talking about, especially when we're focusing on AI or communications, hundreds of billions of computations to process a single image or data set. And so being able to rapidly simulate the true hardware behavior anywhere from 30x for cycle accurate simulation up to 1000x faster than RTL means that you get to simulate in minutes or hours versus hours, days, or weeks. So you can run multiple tests and get your regressions done overnight rather than having to wait a week to run a full set of regressions. And then by modeling in the synthesizable bit-accurate data types, you get to directly measure and observe the effects of quantizing your algorithm. So you get to, try and reduce the precision to the smallest amount possible, and look at the power and basically measure the effects of that quantization. The great thing about the bit-accurate data types then is you're really simulating the true hardware behavior in C++. Or System C. And because the precision can be completely arbitrary, you're not limited to just looking at the effects of doing, whether it's 8 bits, 16 bits, or 32 bits. Precision can be any number of integer and fractional bits. Automatic data flow control is built in. So with complex SoCs, we're going to need to access system memory, we're going to need to access local on-chip memory, and we need the ability to communicate between processes. And so both untimed C and System C provide the user with some predefined protocols that are, the simplest ones are really just data ready valid protocols, and then we have more complex protocols such as like AXI4 master and slave interfaces. So you don't have to specify the protocol in the source, and you just focus on the functionality of the algorithm. But because you're either using a protocol as a constraint or a library for System C, that data flow control is built in, and so it will start and stop the hardware if data can't be read or written. And so because these are simple and consistent protocols, it's very easy now to take that hardware, integrate it into a larger system, and have it work out of the box the first time. And for this presentation, we're going to really focus on the MatchLib interface library, which is a System C library, where instead of doing the protocols as a constraint, we provide a library that describes these protocols under the hood, and you don't have to worry about the implementation. I mentioned that designing, or especially with AI and ML, but most designs require some type of on-chip buffering, and so high-level synthesis makes designing with memories easy. With AI and SoC design, we're going to have lots of local on-chip memories, and Catapult HLS is able to infer a memory, or if you want registers, from C++ arrays. So you don't have to worry about the low-level details. You simply put an array in your design and tell the tool, I want you to infer this as a memory. And then you get to add constraints to say whether this should be a single port or a dual port or a register file. And the memory behavior is described in a Catapult library. And what this means then is that Catapult is going to generate the address data and control to interface to that memory that you've described previously in a Catapult library format. And so assuming that you've described it correctly, and that's quite easy to do, and we have ways to test that, the instantiation and the hookup of the memory is always going to be correct. So again, it doesn't, HLS kind of removes having to worry about those low-level details, and you get to focus on the functionality. Also, if you have arrays internal to the design, you'll end up with instantiated memories or inferable memories if you're targeting FPGA. And if these arrays are on the design interface, Catapult's simply going to generate a memory interface to hook up to an external memory. There are also higher level types of optimizations that you can do with high level synthesis, where Catapult will let you take that memory that you've now inferred from a C++ array and optimize the memory bandwidth using high-level synthesis constraints. So for things like AI, ML hardware, you may require multiple parallel memory structures. And so you can simply go in using a high-level synthesis design constraint and say, make my memory twice as wide in order to read and write more data in parallel. So you can increase your on-chip memory bandwidth. And then you also have the ability to partition a larger memory into a bunch of smaller memories. And so we do this a lot, especially with the AI ML type algorithms, where you might want to take this large array and say split it into 32, 64, 128 small SRAMs in order to be able to read a massive amount of data in parallel. Catapult makes achieving performance and area goals achievable. So Catapult does all of the classic high-level synthesis optimizations. With high-level synthesis, and again, I won't go into detail here, but just to give you an idea, many of the optimizations are done around loops. And so you can perform loop unrolling, which means adding parallelism into your design. You can perform loop pipelining, which is a way to tune the throughput of the design. And then things like having sequential loops in your design, the tool has the ability to do automatic loop merging for independent loops. And this is a way, again, to tune the performance and explore multiple architectures.
Mike?
Catapult, yes.
We got a couple of different questions I thought maybe you might want to think about answering. We thought,
sure.
Yeah, sorry. A couple from Thomas. It says, can you infer dual ported different clock memories? And for a register file, can you do different number of read and write ports?
So for a dual port register clock memory, Catapult would not infer a shared memory. I don't think it'll infer different clocks on a shared memory between.
No, you'd need to instantiate it, Mike.
Yes.
Okay.
Thank you, Stuart.
But there is a way. Thanks.
Yeah, and in System C, memories between processes anyway are instantiated, so you can do whatever you want. In untimed C, a lot of that behavior is hidden under the hood, but definitely we can do multiple processes that run on different clocks, but as Stuart said, you would have to instantiate it.
Okay, thank you.
Okay. Was there a second part to that question, did you say?
It was a different one, but Sudhir is typing the answer to his second one. And then I think maybe just a little bit more on the memories. I've got Mohammed is asking, can HLS support the emerging memory technologies modeling?
I'm not sure. Yeah, I think we would have to maybe take that online because I'm not sure if he's talking about like stacked memories, 3D type structures. That is something that's going to happen on the back end. So for Catapult, remember again, we are producing RTL. We synthesize our output as RTL, and we target memories where you're going to bind in the physical memory during the back-end synthesis and place and route process. And so whatever you can do in hand-coded RTL, we can integrate that into the HLS flow.
Right. Okay, thank you.
Okay. So
Don't forget
a
to
couple.
silence your phone, Mike. I think it's chiming a lot.
Yeah, I did. Thanks. Another really powerful feature of HLS is scheduling. So essentially, high-level synthesis can automatically close timing based on your target technology and the clock frequency constraints specified by the user. And this is super powerful. Some of the case studies that Ellie has provided links for go into this in detail. But what it means then is that when you write your C code, you don't have to worry about pipelining in the classic sense that an RTL designer would do. The tool is going to analyze the dependencies between the different operations in your algorithm, and based on the clock frequency, it's going to insert pipeline registers to give you a design that meets timing. And so this means now when you change technology, whether it's from FPGA to ASIC, or different clock frequencies or different ASIC technologies, you're always going to have a design that closes timing. And then lastly, high-level synthesis is always optimizing the design and trying to reduce area under the hood. So it is performing register and resource sharing automatically, where it'll analyze the different variables in your C design and basically do lifetime analysis, where it can then automatically share variables onto the same register in order to save register area, as well as also it's always trying to save area by sharing operations that are mutually exclusive. And so this is happening all the time under the hood, although we provide the ability to control it as well, so the user can disable it or enable it based on their requirements.
Mike, quick question.
Yes,
On
sure.
the scheduling part, how do we, Santosh has a question, how do we control the levels of pipelining against any latency requirements?
So again, I'm not going to get into the specifics of high-level synthesis optimizations. We'll provide links on that, but there are design constraints, and for the classic high-level synthesis, design constraint is specifying the pipeline initiation interval that lets you tune essentially the throughput of your design. And so we'll provide links for detailed information that gives you kind of the theory behind that, which I also cover in the HLS Blue Book that we'll provide links to.
Thank you.
Okay, a couple other things then, and I think this is enough of a review of HLS. One of the things about high-level synthesis that we've learned, really since we started this, we launched the production version in 2005, I think, of Catapult, is that hardware designers like to know exactly what happened. And so in the past, high-level synthesis, it was somewhat of a challenge because you had to take it on faith that, you wrote your design, you applied your constraints, and you got this hardware out. And it was hard to know how the tool actually did the synthesis process to transform C into RTL. And so we've been working the past couple of years on what's called the Catapult Design Analyzer, and this provides a cross-linked view from all the different kind of views and optimization stages of high-level synthesis. So it shows you your source code, it shows you the synthesized RTL, it gives you different detailed information on the types of hardware resources that were used, as well as how the design was scheduled, and everything's cross-linked. So no matter where I click, it's going to highlight that same view. I click on a multiplier in my RTL schematic, it gets highlighted everywhere. Plus, I can also filter in on a specific section and say, show me for this particular loop, what did the tool actually build? So it's really demystifying what HLS did. And then furthermore, it also provides you actual coding style advice, because with high-level synthesis, because the optimizations are focused around loops, there are good ways and bad ways to code your loops if you're trying to add parallelism. And so the design advisor will directly point out problems in your code and give you kind of the bad way of coding it, and then tell you how to restructure your code so that this synthesis tool can do the best job with it. If you're interested, there are also YouTube videos available, or videos available up on YouTube that cover the design analyzer in more detail. You can build complex multi-block systems. So in System C, it allows you to explicitly specify modules and threads, and really you're explicitly specifying concurrency, concurrent processes. Untime C, even though it is a single-threaded design language, we have the ability to infer not only parallelism, but concurrency as well. And so you can build very complex multi-block systems from either untimed C, where it's inferred, or where with system C, you get to explicitly describe and model and simulate concurrency. And so this is very important, because this is not a tool that is just for building single blocks in your design. It's for building complex systems. Power optimization is very important. So power is going to be critical for most SoC designs, especially anything that's going to be handheld. And Catapult will automatically both analyze and optimize powers. Along with being able to explore area and performance, Catapult will, assuming you've pointed it to your Liberty files, you can just click a button and it'll come back and give you power information for the different architectures that you've explored. So you get to compare area performance and power to get the best possible combination of all three. And then along with the analysis and just reporting capabilities, we also perform automatic clock gating as well as sequential clock gating optimizations. So Catapult runs the PowerPro, the Siemens PowerPro technology under the hood, where it can automatically analyze forwards and backwards through very deep cones of logic and either add or strengthen the clock gates in your design, which it's structuring as enables in your RTL code in order to get the best possible power. And then lastly, because we are creating the data path, we are automatically pipelining the design. So we're automatically adding pipeline registers into the design, which means you may have very deep pipelines with these delay lines through the pipelines, and the tool can automatically transform those delay lines into circular buffers, again, for significant power reduction. And then lastly, I had mentioned this, and this just will lead nicely into the rest of our discussion about when we get to talking about verification. As I said, Catapult's RTL is correct by construction. So what this means then is that because we're a very mature technology tool and we rarely make a mistake, although it has happened, but like I said, 99.99% of the time we get, as a user then, you get to focus on verifying the behavior and the correctness of your synthesizable model in C++ or System C, where you can do it very quickly. And so typically our users will have some type of reference model that may or may not be a bit accurate model. They have a synthesized model, and they spend most of their time proving the correctness here. Then you synthesize the design. You now have RTL, and all you need to do before handing this off to the integration and verification teams is you want to make sure that it actually is behaving as expected. And so Catapult has an automated verification flow for both System C and C++ that is meant to be used by the designer that's driving the Catapult HLS tool to basically sanity check the RTL. And what it does is, for untimed C, we will automatically verify the original C design using the stimulus from the C test bench against the generated RTL. So we automatically capture the test bench stimulus, convert those untimed C transactions into timed pin level wiggles, drive it through the RTL, capture the output, and then do an automated compare and come back with a pass or fail. And then for System C, what we do is that same flow, it works a little bit differently, is we will automatically swap out your System C model with the synthesized RTL. And so you write your testing in your System C test bench, and now that test bench performs the same tests on the RTL. And so this is really meant to be used by the designer to feel confident that he can hand this code off to the downstream teams and not have introduced bugs. So this is kind of a very important step in the HLS design process before we move on to integration and verification. So in summary, SoC design and building these accelerators is just becoming more and more complex. We know that power, performance, and area are all important. And high-level synthesis is really, providing designers today with the ability to get to an optimal architecture quickly and then reap all of the benefits on the verification side of things that we're going to get into in the next part of these presentations.
Okay, thank you, Mike.
Oh, quick poll.
Oh, go for it.
Where is the current bottleneck, if any, in your design flow? Is it in designing the algorithm? Is it in the RTL creation? Is it in the verification and debug? Or is it in the back-end flows, including place and route?
All right, we still have quite a few coming in. Don't forget to hit submit once you've made your choice. I'll end it in a couple of seconds. Okay.
Excellent.
Okay, so verification and debug, which is good because that's going to be the big focus moving forward. One question, and I'm just going to answer this. I see Sudhir is answering it, and I'm assuming this is asking what's more preferred, C++ or System C. And
that's correct, Mike.
Yeah, and so the answer is it depends on what you're trying to do and what your preference is. We have many customers that like doing untimed C++ because it's easier to code. It simulates a little bit faster, though, difference is 300x to 1000x over RTL between the TLM System C and untimed C. But what you will see then is that there are certain things that untimed C does not allow you to do, and either you do them in RTL or you use System C and MATLAB, and that would be building your own complex bus interfaces, doing things like DMA controllers, having arbitration between different processes or arbitrated memories, or modeling things that are non-deterministic where you need non-blocking behavior. So these are all the types of things that you either need to push to RTL in an untimed C++ flow, or as you're going to see, MATLAB allows you to do this. It gives you all of the power of C++, but it gives you these capabilities on top of that and really lets you verify it easily.
Okay, thank you.
All right, thank you.